This short video will describe different relationships of muscular efficiency and one example of calculating out muscular efficiency. And this is typically done on a cycle ergometer or now on a road bicycle with a power meter. So I copied some definitions. Here's a definition for muscular efficiency. And it's during steady state exercise. So we're assuming the VO2 is at steady state. And it's a ratio. So efficiencies, the units are as a percent. So it's a ratio between the work accomplished and the energy expended by that individual. And on a cycle ergometer, it's relatively easy to determine because we can quantify the work accomplished, typically in watts. But depending on the selection of the appropriate baseline, there's some different definitions and different measures of efficiency. So this has led to the development of several methods of calculating an efficiency, and I describe these on the next slide. So just remember that efficiency is energy out divided by energy in. So power output on the bike divided by the oxygen consumption coming in, and it's that ratio of those two. So expressions of mechanical efficiency. There's gross mechanical efficiency, meaning all the oxygen consumption that is being used, both the oxygen consumption to ride the bicycle and the oxygen consumption of resting metabolic rate. The net mechanical efficiency would subtract out that resting oxygen consumption to come up with a net mechanical efficiency. Work efficiency is another definition, and delta efficiency is another definition, looking at the changes in efficiency, so delta for change, between two different submaximal workloads. This next slide shows the measurement for gross efficiency. So gross efficiency indicates the percent of the total chemical energy expended that contributes to the external work being done. So it's work output divided energy expenditure times 100, so it comes out to be as a percent. So this next slide is the equation for gross efficiency and also the equation for net efficiency. Remember, net will subtract out rest. So number one on the top, gross efficiency is work accomplished divided by energy expended. So work W divided by E times 100. Number two, the net efficiency is work accomplished divided by energy expended above that at rest. So here work is divided by a capital E for energy expended minus a small e, the oxygen consumption above rest. So this will subtract out rest. This next slide looks at work accomplished, or work efficiency and delta efficiency, so two other equations to know. So number three, work efficiency is work accomplished divided by energy expended above that in cycling without a load. So work efficiency, there is some oxygen consumption when one is pedaling against zero load. So even though there's no external work being done, there is internal work being done. So it's work accomplished divided by energy expended above that in cycling with zero load. So EL is energy expended loaded and minus EU, energy expended unloaded. The delta efficiency, number four, is the delta work accomplished divided by the delta energy expended. And you can look at the variables on the bottom of this slide. So a couple of different explanations and a couple of different equations to calculate out efficiency. And efficiency is obviously important, just like economy in terms of performance, and various factors can affect muscular efficiency. Typically, a greater work rate equals a poorer or lower efficiency. There's typically an optimal speed for efficiency. There's extrinsic, so outside factors, like, and there's a lot of work being done on this. So, for example, running shoes, or here in the terms of efficiency, bicycle equipment and aerodynamic equipment. Typically, slow twitch or type 1 muscle fibers are more efficient than fast twitch or the type 2 muscle fibers. Typically, more fit people, more aerobically fit people are more efficient. Body composition, a greater percent of body fat would decrease efficiency. And with practice, there's better technique. And so better technique would improve muscular efficiency. So here's an example of calculating out a gross efficiency. And efficiency is calculated out as a percent. So we need to convert we need to convert power into either watts, or here I'm giving an example of kcals, and we need to convert oxygen consumption into kcals. So here's an example of a steady state VO2 of 32 mils per kg per minute on a bicycle. And the power output on the bike at that steady state VO2 was 150 watts. Their VO2 max is 44, 53 kilograms of body mass, and an RER value, so a respiratory exchange ratio of 0.92. So the 32 VO2 max times, or multiplied by body weight, divided by 1,000. So convert that into absolute liters of O2 of 1.69, and then multiply by the caloric equivalent at that RER value. So then multiply by 4.961 kcals per liter of O2. So they would be using 8.41 kcals per minute. So convert VO2 into kcals. Then convert watts into kcals per minute. So 150 watts is 2.149 kcals per minute. And then we're going to divide those out. So 2.149 divided by 8.41 multiplied by 1,000. So a gross efficiency of 25.5%. And actually, that's sort of a typical value. This example of efficiency took into account the caloric equivalent. So depending on fuel utilization, it's not the same efficiency, or it's not the same caloric equivalent. And some examples of estimations of VO2, here's an ACSM equation for running. They assume a caloric equivalent of 5, which is assuming someone is burning all carbohydrates. And these estimation equations are put into tables. So here's a table from ACSM. And over here, based on running speed and body weight, they can come up with a prediction of energy expenditure in kcals per minute. But this again is assuming a steady state of running, and it's assuming a caloric equivalent of 5. And that's not always correct. So here on the left-hand side of this table is the R value, or the RQ or RER value. And here's the kcals per liter of O2 and the percent of carbohydrate and the percent of fat. So if the RER value is 1, that's a caloric equivalent of 5. And this is the assumption that it's 5 kcals per liter of O2. And here is another table that is looking at the same thing. So here's the kcals per liter of O2, and here on the bottom, if the RER value is 1, it's 5 kcals per liter of O2, 100% carbohydrate. But typically, when we calculate out a muscular efficiency or a running economy, we're not at VO2 max, where it's a submax value. So you can look at these examples. Here on the top example, the R value is 0.9, and we're using this caloric equivalent according to this table over here to the left. So here it's 2.21 kcals expenditure. On the bottom example, it's 1.5 liters of oxygen per minute. If we use the constant of 5 kcals per liter of O2, here we get 225 kcals. So it's different. A small difference, yeah, but it's different. And if we're looking at efficiencies or economies, that's an important difference. So in conclusion, we've looked at economy and we've looked at efficiency, and we've looked at now fuel utilization, which can be important in terms of run economy or run efficiency. And newer studies are using either watts per kg or a caloric equivalent to come up with a run economy or an efficiency, and thereby using the caloric equivalent. So this was a short video looking at muscular efficiency and a calculation for muscular efficiency.